Hey everyone, welcome to my little mini video lecture on the SN2 reaction. And the full sort of formal name for that is substitution nucleophilic. And then you're like, where's the two? Well, when we say bimolecular, what we really mean there is there are two molecules in the rate limiting step. More on that to come. But when we say two, what we really mean is bimolecular. So that is where SN2 comes from. And for those who are just getting started in organic chemistry, we may not really know what is a nucleophilic reaction? What does that even mean? Well, let's talk about it. What is a nucleophile? So a nucleophile we like to abbreviate as NUC, nuke. You may see a lone pair on there. It doesn't actually mean anything in terms of elements. It's just a quick abbreviation when we want to be general. So what is a nucleophile? It wants to go out and get a nucleus. Hence why we call it a nucleophile. It's something that wants to go out and get a nucleus. Usually these are going to be things that either have that lone pair of electrons on them or are going to have a negative charge sometimes. And the other thing we think about nucleophiles to sort of anthropomorphize them even more is that they like to go out and attack. So that is how they get the nucleus, by attacking it. So what do they attack? Nucleophiles, having that negative charge or electron density on them, are partially negative, so they want to go after things that are partially positive, and that's where electrophiles come in. We like to abbreviate electrophile with a big capital E, sometimes with a plus sign on it, to show that that is something that has a partial positive or full-on positive charge. And because of that, it wants to get some electrons, which are going to be provided by our nucleophiles. As I already mentioned, these often have a partial positive charge. And similar to my third point up top, they're going to get these electrons from the nucleophiles by being attacked. So again, just anthropomorphizing, that's one way to think about it that I think is pretty accessible to most students. So the last thing that we need to make this SN2 reaction go is a leaving group. So that we will abbreviate as LG for leaving group. And what the heck is a leaving group? Well, it's pretty much the name is what it does. A leaving group is something that leaves. Pretty self-explanatory, right? But what does that mean? In order for it to leave, it must be something that is either an atom or a group, something that's really stable on its own after it leaves the molecule. And so often that means that it can, in the case of SN2 reactions, it can usually stabilize or has factors that will help it stabilize negative charge. And so factors like this could be things like resonance, etc. We can talk more about leaving groups maybe in a different video. So to get down to the big part about this is the SN2 mechanism. So it's not too hard. Arrow pushing can be a little intimidating, I know, but for this one it's pretty simple. Before we get to the arrow pushing, let's go ahead and remember to define our parts here. So we have our nucleophile here. So since that's it's just the name abbreviation, it may not be too difficult to know what that is. But we want to focus on the other groups as well. So there's our leaving group. But what is this carbon that I've labeled kind of in magenta purple here in the middle? That is our electrophile carbon. You might also hear this called Electrophilic Center. So that is the one that is directly attached to our leaving group. Another way to think about the sort of naming or nomenclature, there's a lot of different ways to talk about organic chemistry, but the electrophilic carbon being the one that's directly attached to the leaving group, we also might call the alpha carbon. which will help us out with elimination reactions later on. Now, this is not to be confused with alpha positions in carbonyl chemistry, which can be a different thing. So, for this reaction, the kinetics of this we'll talk about in a second, but since we have this nucleophile that's going to be actually pretty strong and a leaving group that's going to be ready to go and leave, this reaction we think of as a fast, strong reaction that happens all in one step. So we think about our nucleophile as something that wants to attack an electrophile as coming in and drawing our curved arrow formalism to attack right at that purple carbon center. And since we're attacking there, that means that this nucleophile is making a new bond to carbon. So we have to break one in order to keep carbon having only 4 bonds at a time. So that means our leaving group is going to have to do exactly what its name implies and get on out of here. So then we'll redraw our product, where now the nucleophile has come in and made a new bond to our purple carbon here. And we'll just fill this in. Then the other R groups that are around here, whatever they are, we don't really care yet. We'll talk more about those in a bit. But they're still there, just hanging out. Then the leaving group is off somewhere by itself, probably with a negative charge. Depends on what the species is. So we want to think about this as occurring all at once or in a concerted mechanism. We say that because just like when you were, if you were to go to see an orchestra, they play all together in concert, all at the same time. So the nucleophile is coming in at the same time that the leaving group is leaving. We'll have a little bit more about the transition state on that in a minute. So really quickly to talk about the kinetics here, because this all happens at once, and this will go back to our little bimolecular or SN2 note, due to this concerted mechanism, we have to have both the nucleophile and the substrate, or the electrophile. There's a few different ways that you can call our sort of carbon-based reactant of interest. So I like to call it the substrate referring to the whole thing up here, including the leaving group. So the nucleophile and substrate have to both be present at the same time in order for this reaction to happen. So both of their concentrations matter in how fast the rate can go. So in order to get this reaction to go, both of those two species have to be present. They have to contact each other at the same time. And so whether we have a lot of those or a little bit of those, either species is going to affect how fast this reaction can go. So when we talk about a rate law for this reaction, we have some rate constant K that's experimentally determined. Don't worry about that. But we have to take into account the concentration of both the nucleophile and the substrate at the same time. And just a little reminder from Gen Chem is that when we're talking about these, that they're both to the first power because we just need one equivalent of each for this reaction. But the fact that they're both multiplied together makes this a second order or bimolecular reaction. Okay, so let's talk about when we want SN2 to be the mechanism we choose to do these reactions by. So in this unit, there's a lot of deciding between what type of reaction is going to happen. So let's talk about when we choose SN2, and there's a little bit of a spoiler at the bottom of the screen right now. When we have an SN2 reaction, we'll know that because our nucleophile is going to be really strong. We'll talk about what that means in a second. And we also have to have a substrate that allows our nucleophile to come in without too much trouble. So we like to call that an unhindered substrate. So I'm going to put both of these in quotes here because they're sort of relative terms, right? What is strong? What is unhindered? Let's talk about that. So strong nucleophiles are usually what we're talking about when we look at a species that has a negative charge. But that's not always true. There are definitely a couple of exceptions here. So we'll talk about a couple of exceptions in our examples in a minute. The negative charge is important. Another thing that's important is that they're pretty small and sleek or linear types of molecules that don't have a lot of steric bulk to them. We want to think about something that can kind of just get right in there. You might say like a harpoon that can just kind of reach right in and get to its target without having a lot of branchy big things that are just going to slow it down. So let's talk about some examples of those real quick. Right. So one of the examples that we will see a little bit more coming up in the last part of the semester here are any kind of R minus, right? So that's carbon-based groups with a negative charge on them. Things like Grignards or organolithium things, but only as long as they're not bulky. If they're bulky, then they're going to probably do something else more likely than doing SN2. A couple of the big players here are cyanide, which is very dangerous, but it's very useful for doing this reaction. And also things that are useful and not dangerous, but you might not think that it's that important, is remembering your Lewis structures for things like cyanide and our next example. You have to know that the negative charge is on this carbon and is not on the nitrogen. That's really important. The other one is the azide, which you might just see written as N3 minus, but again, here's where the Lewis structures come back in handy. We want to make sure that we can connect up those three nitrogens in such a way that all their octets are satisfied, all that good stuff from Gen Chem. But that gives you a much more complicated structure than you might think because of all these lone pair electrons we have here. We actually have a whole lot of different charges. They end up canceling each other out to make an overall 1 minus. But one of those ends of the azide is going to be a very good nucleophile. Again, these two things, cyanide and azide, are both pretty linear, right? Small. They're very effective nucleophiles to get right into their target. Some of the other strong nucleophiles that you'll see are things like the conjugate bases of alcohol, so OR minuses, and again, S minuses, the thiol version. The big kind of exception here is nitrogen. So nitrogen can actually be quite strong depending on what those R groups are. They can't be bulky. But if they're not bulky, the nitrogen is actually a fairly strong nucleophile due to the fact that it's not super electronegative. It's fairly up there, but compared to something like oxygen, it's really not that electronegative. So it doesn't really mind donating its lone pair electrons to an electrophile. So those ones will actually be stronger than you'd think for something that is neutrally charged. Okay, so that's a bit about nucleophiles. Now let's talk about substrates. So when we say unhindered, what does that mean? It just means that something is going to be easy to get into and attack. So something that doesn't have a lot of complicated other carbon groups around our electrophilic center or our alpha carbon. So our nucleophile's got to be able to get in there quick and easily to attack in this one-step method. Otherwise, we're probably doing a different type of reaction instead. So I want to just draw out a couple of different things here as far as types of substrates. So these are going to be some simple ones, but we'll start with something like this. I'm just going to use the same leaving group of bromide for all of them. So there's a methyl bromide. That's a primary bromide, a secondary bromide, and a tertiary bromide. Just put those labels on. So when we look at the degree of substitution is increasing as we go along. And that's going to change how fast or if our reaction can happen at all. So if we think about something like the methyl group here on the far side, if we were to have something come in, all we have is just hydrogens that are going to be quote unquote in the way of our nucleophile. So they're not very big, they're the smallest thing that we have. It's not a problem for those to just kind of move out of the way so that the bromide can leave. So if we have some kind of methyl leaving group, that's going to be a very fast SN2 reaction. If we have a primary, same idea, that we mostly just have a couple of hydrogens here. There's one carbon group. It's not too bad. This is also going to be fast to do an SN2 reaction. Now, when we start getting to something like a secondary electrophile or electrophilic center, that still can do SN2, but now depending on what these carbon groups are, it's going to be a little bit slower. So it's going to be somewhere on the order of medium to slow. And then if we get all the way to tertiary, now there's just so many big branchy carbon groups in the way that this just actually can't happen. We will not see SN2 happen at a tertiary center. So as I like to write, there's no reaction possible for that. So if you are looking at a tertiary substrate, you want to consider one of the other types of reactivity that we'll talk about in this unit. But SN2 is really only going to happen in this window. Okay, so let's look at some examples now that we've got a few ideas of what our substrates need to look like, what our nucleophiles look like, and how the reaction actually proceeds. So let's look at some examples here. So I'd recommend for you to take a moment to pause the video and take a guess at these for yourself, even if you don't feel like actually pausing and writing this out, even though that's the best way to do it. I recommend just stopping for a second to make a prediction about what's going to happen here. And I'll kind of talk through a little bit of the analysis that I like to do as I approach these problems. So if we're talking about a reaction that looks like this, now that I've kind of spelled it all out for you, hopefully you can see some of where the pieces are. But sometimes professors like myself will be a little bit tricky and will put things maybe in different places than you're expecting. So this big molecule here with the iodine, that has a good leaving group. So let's circle that in blue. It's our leaving group color from earlier. So that is probably our electrophile and our substrate. So we want to look for that carbon that's immediately next to it right here. That is going to be the one that has a lot of that partial positive charge to it. And that's where we're going to attack. And now what are we going to attack with? Our nucleophiles are often positioned over top of the arrow, but that's not always the case. So in this case, hopefully this one rings a bell from a couple minutes ago, we just looked at azide. So this is sodium azide. So the THF, what is that doing there? That's just a solvent. So hang on for that more later. We'll talk quickly about solvents, but don't worry about it for now. For now, let's practice using the other pieces and putting them all together. So we have our nucleophile, we have a leaving group, we have a center that has the partial positive charge on it, that we can go ahead and do this reaction. So we do want to check a couple of things. Is our nucleophile strong? Yes, our nucleophile is strong. It's going to be N3 with that negative charge, so that's good. Is our substrate unhindered? Yes. So if we're looking at this carbon right here, we only have a bond to one other carbon, ignoring our leaving group, right? So this is a primary substrate with a primary leaving group on it. So this should work just fine. And now I'm going to draw in here with red our arrows, because it's always good to practice your reaction arrow pushing. We're going to have the N3 come in from here, attack this carbon, and then that is going to force the bond between our carbon and our leaving group to break and force our leaving group out. So now we can draw the product here, where nothing has changed about this benzene ring. It's just hanging out there. We haven't done anything to that. Our iodine is gone, so that's actually out here. We'll draw it in blue as I minus. And then we had the N3 come in at this carbon here. Let's highlight that in purple again. And we made a new bond to our nucleophile, N3, just like so. Okay, so not too bad, right? Let's look at the next example here on the next page. So for this one, let's again identify all the pieces. It's going to be good practice to identify all the pieces in a reaction because for this video, we're talking strictly about SN2. On an exam, test, quiz, etc., you may be looking at a variety of reactions all mixed together. So you won't necessarily know, okay, I know this is SN2, I'm going to just push my arrows. You may have to do a little bit more detective work to figure what's happening. So I recommend practicing these sort of steps for all of the practice problems that you do. All right, looking at this next one, want to find our leaving group. So there's a bromide, pretty much just using halogens for these examples, but there are other good leaving groups out there. So the bromide is our good leaving group, and then we want to identify the electrophilic carbon right next to it with that partial positive charge. And then thinking about our nucleophile. Do we have a strong nucleophile present? Yes, we do. It's this cyanide from, again, our previous example, Cn-. And don't worry about DMSO for now. That is just our solvent. So let's do our check-in. Cn is a strong nucleophile. We have a good leaving group here, and our electrophilic carbon is a secondary carbon now, so that we have these other two groups, carbon-based groups that are attached to it. So this is getting to the sort of more bulky end of SN2 reactions we can do, but we can still do it here without any problem. So let's go ahead and bring our nucleophile in, attacking at that carbon center. That's going to make a new bond and force this bromine to leave. And that'll give us a product that looks like this. So nothing changed about any of the rest of it. And then our cyanide came in and attacked right here. And then the bromine is off by itself, nice and stable. It's negative charge on its own. Okay, so let's look at this third example, pretty similar. So again, thinking about our leaving groups, chlorine, again, halogen is a good leaving group for this. Let's look for a nucleophile. So normally the nucleophile is here, but what is Bewley? What is that? For those who haven't had your Grignard unit yet, that is butyl. So there's 1, 2, 3, 4 carbons, and then lithium. So when we see this, what I like to think of this as is just butyl chain with a negative charge, and then lithium is off by itself because lithium has low ionization energy. It wants to be an ion. It wants to give up that last electron. So when you have a compound like this one, it's really actually going to perform much more like this ionic version up here. So we like to call that the Ionic Approximation. That's going to be our nucleophile. And then let's think about our electrophile here. So there's our electrophilic center with the partial positive charge on it. Again, there's two groups out to either side. So this is a secondary leaving group, secondary substrate. We are good to go with SN2. So again, let's just practice drawing our arrows. Our butyl chain is going to kind of come in here. And then that's going to, again, break that bond, force that chlorine to leave, so that our product will look something like this. So the chlorine left, and then we added this 4-carbon chain on, so just be really careful. Always numbering your carbons. If that's the one piece of advice you take from this, number your carbons every time. I promise it will save you points. So here's 1, 2, 3, 4. I'm going to number that just to be sure. I literally have to number just so that I can tell that I've done it right. So if I have to do it, I recommend that you do it as well. Okay, so there is our product looking good. Although one kind of question arises that maybe you're starting to see at the bottom of the screen, that we had some stereochemistry happening here. So if we had stereochemistry, what's the deal with the stereochemistry here in our product? Do we care about it? Yeah, we do. So we have to talk about the effect that this type of reaction has on the stereochemistry of your substrate because it does matter. So let's move on to the reaction stereochemistry here. So here's just a little brief overview again of how the reaction works. We have a nucleophile, we have our electrophile with leaving group here, and then the nucleophile attacks, our leaving group is gone at the end. So that's something that we've already looked at. We probably, hopefully, are feeling pretty good about how to push our arrows on this. But I'm going to push the arrows one more time just to kind of hit home one part about how this reaction works. So I've drawn this in a very particular way so that the nucleophile is kind of on the opposite side of the leaving group here. So the leaving group is kind of pointing this direction and the nucleophile is kind of pointing that direction. So that's done very much on purpose so that when this nucleophile comes in, it has to attack from this side of the molecule kind of behind where this leaving group is, so that then the leaving group can get kicked out. And so we like to call this the backside attack. And it has to happen this way for SN2. Absolutely. And we'll talk about more why that is in a second. But the thing that's important to think about is this kind of transition state little drawing that I've left for us here is that in the middle of this reaction, at the highest point of energy, we have something kind of interesting happening where our leaving group is still there, but it hasn't completely left yet, and our nucleophile is coming in, but it hasn't fully bonded yet. So the bonds that these are making to the carbon are kind of tenuous, so this one is breaking, and this one is forming. And then those R groups that I've drawn in our starting material are all still there, but they kind of have to get out of the way as much as possible so that the leaving group isn't crowded and the nucleophile isn't crowded either. So what I'm trying to do is kind of draw these in a plane like so. That's not a very good plane, but the idea is that they exist in one flat plane for just a quick second. So what that does is basically it forces these R groups, whatever they are, to kind of get swept across. And that's why they're sort of pointing to the opposite side of the page than they started, right, in our product. So that sort of sweeping along, the way that those groups have to get out of the way, is what we call an inversion of configuration. So this inversion of configuration happens every time an SN2 reaction happens, literally every time. A lot of the time, that's also going to mean that we have an inversion of stereochemistry. But here's where you should absolutely stop. An inversion of configuration doesn't necessarily mean an inversion of stereochemistry. Often it does mean that, but not always. So you want to be sure and really check yourself if you're asked to assign R and S for your products to just really double check yourself before you make a mistake. So another way to think about this sort of inversion, if this is a little too abstract for you, this is something I like to think about around this time of year when we're kind of changing seasons and the weather's acting up. At least where I am in the Midwest, the weather is always acting up, but especially around this time. So around campus, I see a lot of people when it's starting to get kind of rainy and gross outside, they, carrying around their umbrellas and doing their best that they can to fight against the wind and the weather. But you often do see a lot of umbrellas just totally trashed in the cans on campus. So this makes me think of SN2 because if you're here carrying your umbrella and you're just minding your own business, trying to get to class, then all of a sudden the wind, which is pretty much like our nucleophile, comes in and just attacks the underside or the backside of your umbrella. And we all know what happens when that happens. Your umbrella gets kind of blown inside out. And then after the quote unquote reaction happens, you get something that looks like this, where now your umbrella is all inside out and you can see all those little like support things that are under there that give the umbrella shape. This is what we mean by inversion of configuration. So we really changed the structure, if you will, of our umbrella a lot. We had one configuration over here, the useful configuration. And then we just inverted it to the non-useful or the crappy or maybe even garbage, whatever you want to call it, the not so good configuration. So this happens every time, but why? Why does it have to be that way? Well, perhaps you would have already guessed it. We're talking about orbitals. Orbitals are really important for considering why anything happens in chemistry, but particularly for this reaction, it explains really nicely why the backside attack occurs. So if we do a really simple, kind of simplified sort of MO style diagram for just the carbon, and let me go ahead and highlight this in purple, just the carbon here that is our electrophilic carbon directly attached to our leaving group. So here's our leaving group. If we look at the MOs that hold these two together in a bond, you can think about this kind of sigma bonding orbital, wherein we have a lobe of constructive interference here in the middle that shows that, oh, okay, these two lobes were in phase, they constructively interfere to form the bond. So this is just actually the bond existing. And because it exists, that's the sort of good interaction, the good orbital overlap that is lower in energy. Remember, we're on an energy axis here. So that orbital is going to be filled with electrons. And then for every orbital that we make, or I guess any orbitals that you mix together, you have to get the same number out. So if we're taking an orbital from the carbon and an orbital from the leaving group, that's 2. We have to also make a sigma anti-bonding orbital as well. And the case here is that now the phases of the lobes don't match up, so they can't overlap. So if we were to think about sort of this filled phase orbital trying to interact with this empty phase orbital, now it won't work because they're out of phase with one another. So you can see that there's basically no overlap here, and you get a node between these two atoms, right? So the carbon and whatever the first atom of your leaving group is. And so we think about this as being empty. It's going to be high in energy, right? So we don't want electrons there because then that would force this top scenario to be more true, and that nodal plane would be there, which would weaken the bond considerably. So then if we think about our good friend, the nucleophile, coming in and thinking about how it comes in to form a new bond to our electrophilic carbon, well, that has to happen by putting the electrons that our nucleophile brings into an orbital. And it can't fill an orbital that's already filled. It has to fill this empty orbital at the top with its electrons. So in order to do that, the attack has to come from this side over here, right? Because this orbital lobe is the biggest lobe that's attached to this carbon, and it happens to be pointing in the opposite direction of our leaving group, right? So this is something that kind of blew my mind as a student a little bit, is that when you start to fill in, I'm going to use the green arrows here to represent the nucleophiles electrons. When you start filling in electrons into this anti-bonding orbital, that's how you break bonds. Because now the bonding, sort of favorable energy that's coming from the sigma bonding orbital is getting a bit canceled out by this anti-bonding orbital, and therefore the bond breaks. So that's a little bit of an orbital reasoning to see why we have to have the backside attack, and then why we also have inversion of configuration. So thinking about all of this, let's go back and do that last example again, but consider the stereochemistry more carefully. Okay, so here is that same example from before, and we kind of know what the product was, but now let's draw it in nicely with some stereochemistry. So I'm going to just redraw our carbon scaffold here, and then again, never hurts to practice. Let's draw it in green. Our butyl group nucleophile coming in, attacking our electrophilic carbon, and asking our leaving group to leave. And so then that's going to give us our butyl group at this carbon center here. But before we start drawing anything, let's think about the stereochemistry. So our leaving group chlorine here was on a wedge before it left. So if we had to come in from the back side of that chlorine, we probably came in from the dashed side of the bond. So I like to think about that as having come in from behind, or the dashed side. So there's 1, 2, 3, 4 carbons. Number them. It's always good to do. But then what does that mean about this hydrogen that was left here? So that was in the dashed side at the start of the reaction. So that's what's going to happen with those R groups that I showed earlier. They're just going to get kind of swept along in the course of the reaction, so that when the nucleophile came in from the dashed side, the hydrogen now has sort of swept along and is on the wedged side. So that's going to get kind of pushed forward in this case, in this reaction. And this is probably an inversion of stereo, but definitely an inversion of configuration. So we like to talk about this as a stereo-specific reaction. So what does that mean? Just to reiterate that SN2 always goes with inversion of configuration. And usually this can have some bearing on R and S, but not always. So can affect your R and S designations. Whether or not you have a stereo center, you should still be conscious of this happening every time in the reaction, because when you do have stereochemistry, that's where you really want to be careful about it. So always consider the fact that you could be inverting stereochemistry when you go about answering these questions. So when it comes to actually approaching the stereochemistry in some of these problems, it's not always so easy. I want to give you some good strategies for how you think about the stereo-specific nature of this reaction when it comes to any type of problem. So there's a couple of different strategies for how to tackle them. So I want to give you some tools on that. There's going to be 2 major ways that these types of problems will get presented. And so the difference between those 2 ways that they're presented is just sort of the stereochemistry, or the way your leaving group is represented. So the first one is if your leaving group is on a wedge or a dash. That's kind of the nice, easy case scenario. Or it'll be your leaving group is in the plane of the page. And that's a little bit more tricky, but I've got some good strategies for you to kind of get around getting stuck on that. So let's look at my strategies. I've got 3 of them for you, depending on where your leaving group is. So strategy number 1 is for that first case scenario when your leaving group is on a wedge or a dash. So this is basically the exact same example that we just did. You have a leaving group, it's there. In this case, it is on a wedge. So when that's the case, all you have to do is just put your nucleophile on and swap the wedge or dash to indicate inversion. So to draw that out, we had a wedge here at this carbon, but now we want to swap that for a dash, and then we just have some generic nucleophile here. Again, on your own, practice drawing these arrows so that you get a feel for the mechanism even more. So just swap wedge dash. I like to abbreviate wedge dash with WD for wedge and dash. So that's kind of the easy case. Now we have two other methods, methods number 2 and number 3. They're both used for the same case of when the leaving group is in the plane of the page. So when that's the case, it's a little harder to represent inversion. At least you can't do it quite as directly. And there are a lot of ways to kind of go about this. So when the leaving group is in the plane of the page, you have a couple of different options for how you want to represent inversion. So I recommend you to look at methods 2 and 3 and then just pick the one that you like the best and stick with it, because the kind of having both of them jostling around in your brain might make it liable for you to get them mixed up, and then you'll end up with a wrong answer. So look at them both and then pick one and just stick to it. Okay, so the first method, when you have a leaving group in the plane of the page, so here we can see now that iodine is just on a regular solid line, no wedge, no dash. So this is what I call the sweep method. I'm gonna draw in the arrows for this one to help illustrate what the sweeping does. So this is a little bit like what we talked about earlier for the backside attack. Our nucleophile is going to come in from the backside, and I most often like to draw the arrows so that I can picture it that way in my head, and our leaving group leaves. So when we talk about the sweep method and drawing our product, so in the sweep method, I like to draw the nucleophile in as though it had just come from the backside, or approximately 180 degrees. So if this had truly come in from the backside, the nucleophile would be coming in kind of from this direction. And we then think about having our groups, our random R groups here, as just getting swept along, but not changing their wedge or dash, right? So for the sweep method, you have your nucleophile drawn in as though it came from, basically 180 degrees away from our leaving group. And then you just move the other groups along so that you have a nice drawing, right? But you do not change the wedge or the dash at all. So that's the sweep method. Now the next method that again can act as a counterpart to the sweep method, if you prefer this, the direct swap method is maybe more direct, you could say. So same idea is that we have our nucleophile coming in the exact same way, and you can see, can't fit them on the same page, but this is the same starting material that we used in the example number 2. So for the direct swap method, I'm going to cheat a little bit actually and even just copy and paste this over here, because all we need to do is directly swap our leaving group for the nucleophile. And when we do it that way, we haven't really represented the inversion at all. It would just look like, oh, it's the same thing. So we have to change the wedge dash on our other R groups, whatever they are, to represent the inversion that way. So for the direct swap method, directly replace the leaving group with your nucleophile group and swap the wedge and dash. Okay, so if I take this product here and compare it to the product we made above, They don't really look the same. So how can we know? It should be the same reaction, right? We reacted with the same conditions, but are they the same? Let's find out. So I'm going to copy and paste both of these answers down into this next section here. And what that's going to allow us to do is it's going to allow us to compare the stereochemistry of both of them so that we can confirm that, in fact, these are the same two products. All right, let's make this one a little bit smaller. There we go. Okay. So a little foray back into R and S nomenclature for some of those who may be a little rusty at it. Definitely give that a good practice. Let's go to it. Let us just say that the nucleophile is the highest priority thing. We don't know what it is, but let's just say that it's priority number 1 in both cases. I'm going to assign both priorities at the same time, and then we'll think about R and S. So then we have a phenyl group, a methyl group, and don't forget the other thing here that's important is that last hydrogen. It's still there. We need to think about it. So that is definitely going to be our number 4 priority thing here. And then if we have to decide between methyl group and phenyl group, it's both carbon and carbon, because remember, we're always just looking at one atom at a time, so that's the first atom of our methyl group there. But the methyl group has more bonds to hydrogen on it, whereas the phenyl group has all bonds to carbon. So that's higher priority. So that's going to be priority number 2. The methyl group will be priority number 3. Go back and review your R and S nomenclature to get a little refresher on this if this doesn't feel comfortable. So now we want to figure out whether these are R or S. So going from 1 through 2 to 3 and see which way that arrow goes. So 1, 2 to 3 is going that way. So this is the wrong way to go around the clock or the silly way to go around the clock. So that's S. And then if we look here, we have 1, 2, 3. Now that looks like the right way to go around the clock, doesn't it? But you're not allowed to assign that yet because our number 4 group is coming right out at us. This needs to be back behind the plane of the page, right? So what you can do is assign this, it looks like R, but then you have to flip that designation, it's actually S. So, turns out that even though these two products don't necessarily look like they're the same thing, they look like they might be enantiomers of one another. You can always check that by doing R and S, and both of these methods will give you the identical answer, the S stereoisomer. So, either way, your product is going to be the S isomer. And just to hit home about the inversion of configuration, let's take the starting material and bring that down for a little bit of analysis as well. So iodine is going to be our top priority, and then we know the other priorities from our previous designations. So now if we go around here from 1, 2 to 3, that is actually R, and now our lowest priority group is in the back, so that was indeed R to start with. So you can see that we've inverted the stereochemistry when we went from starting material to our products, either case with either method. So like I say, pick your favorite method, whether that's the sweep or the direct swap, and stick to it. It's going to help you out a lot. And then when you have a leaving group on a wedge or dash, you can use method number 1. That's not a problem, easy peasy. So just quickly, a last couple of thoughts for you about solvents in SN2. So I highlighted a couple of them previously and said we'll come back to it, and now we're back to it. A lot of emphasis can be placed on the solvents for these type of reactions. I want to go ahead and say this, I'll give another little disclaimer at the end, is that solvents are important in these reactions, but they are by far not at all the most important thing. You want to be looking at the quality of your nucleophile and your electrophile first and foremost. And then maybe you can think about the solvents to help you decide in a tough case. But for the most part, they're just going to be there. They play a role in the reaction, but it's not something that we're worried about for the most part. So we want to think about different types of solvents that are good for SN2 or bad for SN2. So first and foremost, the good ones. We want things that are going to be polar solvents, but that they are aprotic solvents. So that means no OH, no NH type of bonds. Those are going to be protic solvents. And those ones are not so good for SN2. So those are our polar protic solvents. So let's give some examples of each of those. We've got a lot of favorites here. Things like we saw DMSO earlier, that's this. So we can see there's no OH bonds there, but it is pretty polar if we think about a dipole like so. Another common one, acetone, which is just kind of the carbon version of DMSO. We have DMF, or dimethyl formamide, or amide, whatever you like. Diethyl ether. You might see it as ET2O. That one is going to be really common for carbon-based groups when you're doing something like a Grignard. We often make Grignards in ethereal solvents like diethyl ether or THF, which is just a cyclic ether. That's another good one as well. So those are some good polar aprotic solvents that are going to help our SN2 reactions go quickly. The ones that are not so good for SN2, the protic ones, are going to be things like water, methanol, basically anything that's an alcohol solvent. Anything that has those OH bonds in it is no good for SN2. So why is that? Well, when we think about our nucleophiles, often they're going to be salts, right? So this sodium cyanide or sodium azide, etc. We want to be able to make sure that we can solubilize those salts, which polar aprotic solvents can do, but not solubilize them too well. If we solubilize too strongly, like you do for, let's say I'll just draw water here. With polar protic solvents, they're going to be attracted really strongly to these charged species, right? So we'll draw some on the cyanide, and here's some on the sodium. These interactions with those charged species are going to be really strong in polar protic solvents. These are sort of like an ion dipole type interactions. And what that does is it's fine for the sodium, we don't really care about that, but our cyanide is our nucleophile. If it's kind of like surrounded by all of these hydrogen bond donating water or alcohol molecules, then it's not going to be as freely, readily available to go out and attack the electrophile. Whereas for something like a polar aprotic solvent, they're going to help solubilize enough, but the interactions are going to be weaker because the dipoles are a little bit weaker. So in that case, it's going to be a lot easier for the solvents to just get out of the way so that our nucleophile can go on and do its attack. But I do want to reiterate what I said at the top of this section, is that while the solvents do play a role, they're absolutely not the first thing that you should be looking at. There are way more important factors that you should consider first. If you are asked to provide the reagents for an SN2 type reaction, you want to pick from the list of good solvents here above and not from these ones over here. But most of the time, professors like myself are putting the absolute least emphasis on the solvent. We want to see all of the other factors, things like nucleophile strength and making sure that you get your stereochemistry. Those are the really big things that we want to make sure that you're understanding. So don't stress too much about solvents. Just do a lot of practice problems and get really comfortable with the mechanism and inverting that configuration. And if you have any questions, feel free to leave them in the comments. Otherwise, I'm out, and stay tuned for more videos on the other types of reactions in this unit. Thanks for watching.